So let me try to explain it. So you have a positive estuary, and on average, the salinity field that you have in your positive estuary doesn't change. It has reached a steady state. Okay? The salinity changes along your estuary from low salinity water near the river source and seawater near the ocean, and the distribution is the consequence of both advection and diffusion, and it is a balance in the end. So now if you have a pollutant source, a dissolved substance that you introduce continuously, the distribution that you get in the end should be similar to the salinity distribution, because your pollutant underlies the same physics that the salinity field responds to. Okay, that's the idea. So now if you're in the middle of an estuary and you inject a pollutant, this is the pollutant point source in this diagram. Now it depends on which direction you go. Okay? Because the salinity only decreases as you go towards the river, as you go towards the ocean, it actually increases. So you have to change a little bit what do you consider as a reference? Is this the salinity content that diffuses, or is it the freshwater content that diffuses? And this is shown in this little sketch. So you have to use the concept. It's based on the same concept, but you have to flip. What do you consider, the salt content or the freshwater? And show you one example of how this works. Okay? So consider this example of an estuary where you have measured the salinity along the estuary, and this salinity distribution can be expressed by a salt fraction. Okay, it's the amount of seawater that contributes to your mixture, and the freshwater fraction. This is how much zero salinity water do you need to make your mixture. Again, this can be now shown in a diagram. As you are at the river mouth here on the left side, the freshwater fraction is 1, meaning 100%. And then the freshwater fraction decreases as you go towards the ocean. At the ocean, it is 0, because there's only seawater. And similarly, or actually opposite, the saltwater fraction is 100%. It's 1. Okay? The decimal fraction is 1 in the ocean, and then it decreases to 0 as you go upstream on the river end of your estuary. The sum of both fractions has to be 1. You add up the green and the blue curve in this diagram, you reach a 1. Just means based on volume conservation. Okay? So now we have that distribution. So now if you add a discharge, okay, a point source discharge at any location you want, you can predict the resultant distributions, okay, based on these curves. And I'll show you one example on the next slide. Okay? So for example, you have one outlet here with the orange curve. You plan to build an outlet here in this. Okay? And now you have to base your steady state distribution that you get in the long run, either on the blue curve, which is the saltwater fraction as you move up stream, your estuary, or the freshwater fraction, which is the green curve as you move down towards the ocean. Okay, and you have to rescale your distributions so that you essentially this blue curve here is scaled up so that you get the concentration at the discharge. Okay? Similarly, the green curve has to be scaled up so that you get the concentration at the discharge. And from that, you can predict resultant concentration profile, both upstream and downstream in your estuary. What you need to do is you need to measure the salinity field in your estuary. And there's a second example shown here, okay, which has a lower concentration at the discharge. Okay. Lower concentration, and again, you scale the resultant distribution is proportional to the saltwater fraction as you go upstream and to the freshwater fraction as you go downstream. And with this model, you can actually play around. Okay, you can place your pollutant locations at different parts and see what happens. And this method only works, you can only get a vertically integrated information. So it does not work on, because you have stratified flows, and it's not assuming that you have a surface or a bottom discharge or so. This one is just a very coarse estimate within a positive estuary of what profiles do you get in the end. That's fascinating, isn't it? It's a very simple but very powerful method to predict long-term distributions of a conservative pollutant.